Hello and welcome to the Sleepy Astronomer. I'm so glad you found your way here. Tonight, we aren't simply stargazing. We're exploring something stranger, something invisible, something that makes up most of the universe, yet refuses to reveal itself to light. Tonight, we're drifting through 100 gentle facts about dark matter, the mysterious substance that fills space, anchors galaxies, and makes the universe possible. It doesn't emit light, it doesn't absorb light, it doesn't reflect light, and yet, without it, nothing we see would exist. If this is your first journey with me, welcome aboard. And if you've travelled with me before through the quiet wonders of space, it's wonderful to have you back among the stars. If this exploration helps you unwind or fills you with quiet wonder as you drift towards sleep, feel free to give the video a like. And if you'd like to help others discover these peaceful cosmic journeys, a subscription truly helps this little corner of the universe grow. So, settle in, find your most comfortable position and let your thoughts drift as we begin our gentle journey through 100 facts that reveal mysteries, numbers that deepen wonder, and truths about the invisible foundation beneath all of creation. Here's a fact that should make you pause. When you look up at the night sky tonight, when you see the moon and stars and the soft glow of the Milky Way, you're seeing less than 5% of what's actually there. Everything we can observe with any telescope ever built, every star, every galaxy, every glowing nebula, represents just a tiny fraction of the universe. The rest? Invisible. Not hidden behind something, not too far away to see. Actually, fundamentally invisible. Most of the cosmos refuses to reveal itself to light. Astronomers have a name for this unseen mass. They call it dark matter. Two simple words for something that makes up most of the universe. Dark because it doesn't shine. Matter because its gravity pulls on everything around it. It's there, somewhere, filling space in ways we can barely understand. We know it exists, not by seeing it, but by watching what it does to the things we can see. Dark matter doesn't emit light. It doesn't absorb light. It doesn't reflect light either. In every way that we've learned to observe the universe, dark matter remains silent. Our eyes can't find it. Our telescopes can't capture it. And yet, without it, nothing would make sense. The galaxies we see, the stars that fill the sky, they all behave in ways that only work if something invisible is holding them together. Its gravity shapes everything. Galaxies spiral because dark matter anchors them. Clusters of galaxies hold together because dark matter binds them. The entire cosmic web, that vast structure of filaments and voids stretching across billions of light years, follows the invisible architecture that dark matter laid down long ago. Gravity is the only language dark matter speaks, and through that language it writes the structure of everything. Without dark matter, galaxies would fly apart. The stars spinning at their edges move too fast. By all the rules of physics we know, they should be flung into space like water from a spinning wheel. But they don't fly away. They stay. Something unseen holds them in place. Something with enough mass to keep even the fastest stars bound to their home. Without this invisible scaffolding, the universe as we know it wouldn't exist. There would be no galaxies, no stars clustered together in spirals, just scattered, drifting matter lost in the dark. In 1933, a Swiss astronomer named Fritz Zwicky was studying something called the Coma Cluster. It's a collection of galaxies, more than 1,000 of them, all bound together by gravity. Zwicky was trying to understand how fast these galaxies were moving. He measured their speeds, did the calculations, and found something strange. The galaxies were moving much too fast. Based on the visible matter he could see, all the stars and gas The cluster should have torn itself apart long ago. He calculated how much mass would be needed to hold the cluster together. The number was startling. There had to be far more mass than anyone could see, hundreds of times more. Zwicky proposed something radical. He suggested that most of the cluster's mass was invisible. He called it dunkle Materie, German for dark matter. It was a bold idea, maybe even a desperate one, but it was the only explanation that fit the numbers. Most astronomers dismissed his idea. It seemed impossible. How could the universe be full of matter we couldn't see? How could something so fundamental have gone unnoticed? Zwicky's suggestion was too strange, too uncomfortable. It challenged the assumption that what we see is what exists. And so, for decades, the scientific community largely ignored him. Dark matter was filed away as an odd footnote, a curiosity mentioned in passing, but never seriously pursued. The mystery would remain largely ignored for nearly 40 years. Zwicky had found something real, something profound, but the world wasn't ready to listen. It would take a new generation of astronomers, new tools, and new observations before the invisible universe could no longer be denied. Sometimes the most important discoveries are the ones we're not prepared to accept. Sometimes the truth waits quietly in the margins of a dismissed paper, patient as the turning of galaxies until the right moment arrives. In the 1970s, an astronomer named Vera Rubin did something elegantly simple. She measured how fast stars move at different distances from a galaxy's centre. Just measurements, just careful observations of rotation speeds. She pointed her spectrograph at spiral galaxy after spiral galaxy, collecting data that would quietly revolutionize our understanding of the universe. Sometimes the most profound discoveries come not from complex theories, but from patient measurement of something everyone assumed they already understood. She found that stars at a galaxy's outer edge moved just as fast as stars near the centre. This shouldn't happen. It violates what we know about how things orbit. When planets circle the Sun, the ones farther out move more slowly. Mercury races around in just 88 days. Neptune takes 165 years. That's how gravity works. The farther you are from the mass pulling you, the slower you should move. Galaxies should behave the same way. Stars near the bright centre should spin quickly. Stars at the dim edges should drift along more slowly, taking their time. But they don't. The outer stars keep pace with the inner ones, spinning just as fast, even though they're much farther from the galaxy's centre. According to the physics we know, this makes no sense, unless something invisible is adding mass, unless there's more gravity out there than we can see. The stars at the edge aren't just orbiting the visible matter in the galaxy's bright disk. They're responding to something larger, something that extends far beyond the light. Her rotation curves provided the clearest evidence yet that dark matter was real. A rotation curve is just a graph showing how fast things orbit at different distances. For a galaxy, it should slope downward as you move outward, like a hill rolling down to flat ground. But Rubin's curves stayed flat. They didn't drop. They held steady, sometimes even rising slightly, all the way to the edge of her measurements. Every curve told the same story. There's mass out there, lots of it. We just can't see it. Galaxy after galaxy showed the same pattern. Rubin didn't study just one spiral. She studied dozens. Different sizes, different brightnesses, different orientations, and every single one required invisible mass. The pattern was consistent, undeniable. If one galaxy behaved strangely, you might call it an anomaly. But when they all do it, when every spiral you examine tells you the same thing, you have to listen. The universe was speaking clearly. We just hadn't been paying attention. Gravitational lensing observations showed space bending more than visible matter could explain. Light travels in straight lines, mostly. But when it passes near something massive, gravity bends its path. Einstein predicted this, and astronomers confirmed it by watching starlight curve around the sun during an eclipse. The same thing happens on much larger scales. When light from a distant galaxy passes through a cluster of galaxies on its way to us, that cluster's gravity bends and distorts the image. We see arcs, rings, sometimes multiple copies of the same galaxy stretched across the sky. By measuring how much the light bends, astronomers can calculate how much mass is doing the bending. And here's the thing, the distortion is always stronger than the visible matter can account for. Always. The galaxies we see in the cluster, all their stars and gas, they're not massive enough to create the lensing we observe. Something else is there, something with tremendous mass, warping space invisibly. It's dark matter again, revealed not by light, but by the way it curves the path of light passing through. The cosmic microwave background carried temperature fluctuations that indicated dark matter's presence in the early universe. About 380,000 years after the Big Bang, the universe cooled enough for light to travel freely for the first time. That light is still out there, stretched by cosmic expansion into microwave wavelengths, filling the sky in every direction. We call it the cosmic microwave background, and it's remarkably uniform. Almost the same temperature everywhere. Almost. There are tiny fluctuations, subtle hot and cold spots, variations of just a few millionths of a degree. Those tiny ripples are incredibly important. They're the seeds of everything that came later. Regions that were slightly denser pulled in more matter, and eventually became galaxies and galaxy clusters. Regions that were slightly less dense became voids. By studying the pattern of these fluctuations, their size and spacing and intensity, astronomers can work backward to understand what the early universe was made of. And the pattern only makes sense if dark matter was already there, already clumping, already laying down the gravitational framework that ordinary matter would later follow. By the 1980s, multiple independent lines of evidence were converging on the same conclusion. Rotation curves said dark matter exists. Gravitational lensing said it exists. The cosmic microwave background said it exists. Computer simulations of galaxy formation only worked if you included it. Measurements of galaxy clusters, studies of large-scale structure, observations from radio telescopes and optical telescopes and X-ray satellites, they all pointed the same direction. Science is strongest when different methods lead to the same answer. When astronomers looking at completely different phenomena all find the same invisible signature, you start to trust what the universe is telling you. Dark matter wasn't a wild guess anymore. It was becoming a necessary part of the story, written into the sky in a dozen different ways. Computer simulations could only recreate the universe's structure if dark matter was included in the equations. Astronomers like to build models. They take what they know about gravity, expansion, and the early universe, then run simulations forward in time to see what emerges. Without dark matter in the code, the simulations produce a universe that looks nothing like ours. Galaxies don't form properly. Structure doesn't develop the right way. The cosmic web never takes shape. But when they add dark matter, when they let it clump first and pull ordinary matter into its gravitational wells, suddenly everything works. The simulation grows galaxies. It forms clusters. It creates the large-scale patterns we actually observe. The universe on a computer screen starts to look like the universe outside our window. By the 1990s, most astronomers accepted dark matter as real. It took time. Science moves carefully, and it should. But after decades of observations, after Zwicky's dismissed calculations and Rubin's rotation curves, after gravitational lensing and cosmic microwave background measurements and computer simulations all pointed the same direction, resistance faded. Dark matter wasn't a fringe idea anymore. It was part of the standard model of cosmology, written into textbooks, assumed in research papers, accepted as one of the fundamental components of reality. We still didn't know what it was. We still don't, but we knew it was there. Calculations show dark matter makes up about 27% of the universe's total mass energy. When cosmologists add up everything in the universe, they're not just counting matter, they're counting all forms of energy, because Einstein taught us that mass and energy are two sides of the same coin. When you do the accounting, dark matter represents about 27% of the total, more than a quarter of everything. That's a substantial portion of reality, sitting there invisibly, holding galaxies together, shaping the cosmos on the largest scales. It's strange to think that more than 1/4 of existence refuses to interact with light. Ordinary matter, everything we can see and touch, is only about 5%. Think about everything you can see. Stars, planets, nebulae, galaxies, the moon hanging in tonight's sky, your own hand in front of your face, every atom in your body, all of it, every bit of normal matter in the entire universe, represents just 5% of what exists. We are made of the minority substance of the cosmos, the rare stuff, the glowing exception in a universe dominated by darkness. Ordinary matter is actually extraordinary in its rarity. We are the strange ones in this universe, not the dark matter. The remaining 68% is dark energy, which drives the universe's accelerating expansion. So dark matter accounts for 27%, ordinary matter for 5%, and that leaves most of the universe still unaccounted for. The missing 68% is something even stranger than dark matter. Astronomers call it dark energy, and it behaves like a kind of anti-gravity, pushing space itself apart, causing the universe's expansion to accelerate rather than slow down. Where dark matter pulls things together, dark energy pushes them apart. Together, these two invisible components make up 95% of the universe. We live in a cosmos we barely understand, surrounded by forces and substances we cannot directly observe, in a reality far stranger than our ancestors ever imagined. Every galaxy sits within a vast halo of dark matter, extending far beyond its visible stars. When you look at a picture of a spiral galaxy, you're seeing the bright disk, the glowing arms, the concentrated starlight, but that's just the visible part. Surrounding it, stretching far beyond the last faint stars, is an enormous sphere of dark matter. A halo. It's not bright or colourful. You can't photograph it. But it's there, holding everything together, providing most of the galaxy's mass. The visible galaxy is like an island of light floating in a dark ocean, or maybe like a small campfire surrounded by a vast invisible sphere of warmth you can feel but cannot see. These dark matter halos act like invisible scaffolding, holding galaxies together. Without them, galaxies would be unstable. The stars would drift apart. The spiral structure would unravel. Everything we find beautiful about galaxies, their shape and structure and coherence, exists because of this invisible framework. Dark matter doesn't just accompany galaxies, it defines them. It came first, clumping in the early universe, creating gravitational wells into which ordinary matter fell. Stars formed in those wells. Galaxies took shape within that architecture. We are living inside a structure we cannot see, held together by a substance we do not understand, floating through a universe that is mostly hidden from us. And somehow, despite all we don't know, we've figured out that it's there. That might be the most remarkable part of this whole story. Dark matter formed the first gravitational seeds in the early universe. In the beginning, just after the Big Bang, the universe was remarkably smooth. Almost uniform. Almost. There were tiny density fluctuations, subtle ripples in the fabric of space where matter was just slightly more concentrated. Dark matter responded to these ripples first. It doesn't interact with light or radiation, so while ordinary matter was still caught up in the hot plasma of the early universe, dark matter could already start clumping together, pulled by its own gravity into denser and denser concentrations. These clumps became seeds, small gravitational wells waiting to be filled. Its gravity pulled ordinary matter, hydrogen and helium gas, into these seeds. Eventually the universe cooled enough for ordinary matter to move freely, and when it did, it followed the gravity. Hydrogen and helium gas drifted into the wells that dark matter had carved out. The invisible had prepared a place for the visible. Like water flowing into valleys, ordinary matter accumulated in the deepest gravitational pockets, gathering where dark matter had already laid the foundation. Without dark matter's head start, this process would have taken much longer. Maybe too long. Maybe galaxies wouldn't have formed at all. These clumps eventually became the first stars, then galaxies, then galaxy clusters. As gas fell into the dark matter wells, it compressed and heated. In the densest regions, it grew hot enough for nuclear fusion to begin. The first stars ignited, burning bright in a universe that had known only darkness. Those stars gathered into the first galaxies, small and irregular at first, then growing larger through mergers and accretion. Galaxies found each other, pulled together by gravity, forming groups and clusters. Everything we see today, all the light in the cosmos, traces back to those early seeds that dark matter planted billions of years ago. The universe's large-scale structure follows dark matter's invisible distribution. When astronomers map where galaxies are located across vast distances, they find something remarkable. Galaxies aren't randomly scattered, they form patterns. They line up along filaments, cluster at intersections, and leave enormous empty regions called voids. This isn't chaos, it's structure. And that structure, that cosmic architecture, follows the distribution of dark matter. Where dark matter concentrated, galaxies formed. Where it remained sparse, voids remained empty. The visible universe is like a constellation drawn by connecting invisible dots. Computer simulations reveal a vast cosmic web, filaments of dark matter connecting everything. When astronomers run simulations of cosmic evolution, letting billions of years unfold in fast forward, they see something breathtaking emerge. A web, not scattered randomness, but organized structure. Filaments of dark matter threading through space, connecting galaxy clusters like strands in a vast neural network. The cosmic web is one of the most beautiful structures in nature, and it's completely invisible. We can only see it through simulation and inference, watching how visible matter traces the invisible architecture beneath. It looks almost biological, almost alive, with tendrils reaching across billions of light years. Dark matter could be cold, moving slowly, or hot, moving near light speed. The behavior of dark matter depends on how fast it moves. If dark matter particles are massive and sluggish, drifting through space at relatively low speeds, we call it cold dark matter. If the particles are light and zippy, racing around at speeds approaching light, we call it hot dark matter. The names are a bit misleading. They're not about temperature, really, but about velocity. And velocity matters because it affects how dark matter clumps. Fast-moving particles spread out. Slow-moving particles stay together. The kind of structure that forms depends on which type dominates. Cold, dark matter best matches what we observe in the universe. Hot, dark matter, like neutrinos, moves too fast to settle into the small-scale clumps we need to explain individual galaxies. It would create structure only on very large scales, smoothing out the finer details. But cold, dark matter behaves differently. It can clump on small scales, forming the halos around galaxies, the dense cores of galaxy clusters, all the intricate structure we actually see. When astronomers compare simulations of cold, dark matter with observations of the real universe, the match is striking. The shapes line up, the distributions agree. Cold, dark matter seems to be what we're dealing with. Cold, dark matter clumps together on small scales, explaining why galaxies are stable. This is important. If dark matter were too hot, too fast, galaxies couldn't form properly. There wouldn't be enough concentrated mass to hold them together. Stars would drift apart, spiral structure wouldn't persist. But cold, dark matter, moving slowly and clumping tightly, provides exactly the kind of dense, stable halos that galaxies need. It settles around them like an invisible cocoon, creating a gravitational anchor that holds everything in place. The fact that galaxies exist at all, spinning peacefully for billions of years, tells us something about the nature of the dark matter surrounding them. It has to be cold, it has to be slow, otherwise we wouldn't be here to wonder about it. Warm dark matter remains a possible alternative moving at intermediate speeds. Between cold and hot lies another possibility. Warm, dark matter. Not as sluggish as cold dark matter, not as frenetic as hot. Somewhere in between. It would move faster than cold dark matter, but not fast enough to completely smooth out small-scale structure. The universe it creates would look subtly different, with slightly fewer small galaxies, slightly smoother distributions at certain scales. It's still a candidate, still possible, though most evidence points toward the cold variety. The universe may yet surprise us. We're still learning which speed, which temperature, which type of invisibility fills the space around us. Hot dark matter, like neutrinos, moves too fast to form enough structure. Neutrinos are real particles we've actually detected, tiny, nearly massless, flooding through the universe in enormous numbers. They barely interact with anything, passing through planets and stars as if they weren't there. For a while, astronomers wondered if neutrinos could be the dark matter we were looking for. But there's a problem. Neutrinos move at nearly the speed of light. They're hot dark matter, and when something moves that fast, it can't settle down into the tight clumps needed to form galaxies. It spreads out, smooths over, refuses to concentrate. Neutrinos exist, certainly, but they can't explain the structure we see. They're too restless to build the universe we live in. Every galaxy is surrounded by a spherical halo of dark matter. Picture a galaxy. You're probably imagining a flat disk, spiral arms, maybe a bright bulge at the center. That's the part that shines. But surrounding that visible disk, extending far above and below it, stretching outward in all directions, is a vast sphere of dark matter. A halo. It doesn't glow. It doesn't emit any radiation, but it's there, massive and invisible, cradling the galaxy at its center. The visible part of the galaxy is just a small, bright core floating within something much larger, much more massive, and completely hidden from view. These halos extend far beyond a galaxy's visible stars. The stars you can see, the gas clouds that glow in photographs, they trace out the inner region of the galaxy. But the dark matter doesn't stop where the light ends. It keeps going. It stretches outward, growing more diffuse, but never really stopping, blending gradually into the space between galaxies. Some estimates suggest these halos can be 10 times wider than the visible galaxy they surround. The Milky Way's bright disk might span 100,000 light-years, but its dark matter halo could extend for 1,000,000 light-years or more, reaching far into the darkness, invisible fingers of gravity holding everything together. The Milky Way's dark matter halo may stretch 300,000 light-years or more from the galactic center. Our own galaxy sits within one of these halos. The stars, the nebulae, the spiral arms we can photograph. They occupy the central region, but the dark matter extends much farther. Current estimates suggest it could reach at least 300,000 light-years from the center, perhaps even farther. That's 3 times the width of the visible disk. We live in the inner part, where stars are common and light is abundant, but the halo surrounds us, stretching out into space far beyond the last faint stars, defining the true size and shape of our galactic home. Our galaxy's satellite galaxies, like the Magellanic Clouds, trace the shape of this invisible halo through their orbits. We can't see dark matter directly, but we can watch how things move through it. The Milky Way has several small companion galaxies orbiting around it. The large and small Magellanic Clouds are the most prominent, visible from the southern hemisphere as fuzzy patches of light. These satellites orbit through the Milky Way's dark matter halo, and their paths tell us about the halo's shape and mass. By tracking their motion, astronomers can map the invisible. The satellites are like boats on a dark ocean, their wakes revealing currents we cannot otherwise see. Right now, as you read this, you're inside the Milky Way's dark matter halo. Here's something to contemplate. You are floating inside a dark matter halo right now. Not metaphorically, actually. The Milky Way's visible disk, all its stars and gas and dust, sits at the center of a vast sphere of invisible matter, and we're inside that sphere. Earth, the sun, the entire solar system. We're swimming through dark matter this very moment. It surrounds us, permeates the space between stars. Most of the mass holding our galaxy together is invisible, and we live immersed in it like fish in an ocean we cannot see. Dark matter particles may be passing through your body constantly without interacting. If dark matter is made of particles, and most scientists think it is, then those particles are everywhere. They fill space. They're here in this room, and because they barely interact with ordinary matter, they pass right through everything, through walls, through planets, through you. Every second, countless dark matter particles might be streaming through your body, moving at hundreds of kilometers per second, slipping between atoms without touching anything, ghosts passing through the solid world. You wouldn't feel them. They leave no trace. But the possibility is there, quiet and strange. You might be more porous to the universe than you think. The leading candidate for dark matter is a new kind of particle called a WIMP, weakly interacting massive particle. Physicists have a candidate in mind. They call it a WIMP, which stands for weakly interacting massive particle. The name is a bit unfortunate, maybe even slightly amusing, but it describes exactly what they're looking for. A particle that's massive enough to account for dark matter's gravitational effects, but interacts so weakly with ordinary matter that it's almost impossible to detect. WIMPs would pass through normal matter as if it weren't there, only occasionally, very rarely, colliding with an atomic nucleus. These collisions would be so infrequent, so subtle, that detecting even one would require extraordinary patience and incredibly sensitive instruments. But if WIMPs exist, they could be the answer we've been searching for. Another candidate is the axion, an ultralight particle that could fill space like a fog. If WIMPs are one possibility, axions are another. They're completely different in nature. Where WIMPs are massive and heavy, axions are incredibly light, almost weightless. They wouldn't stream through space like bullets. Instead, they'd fill it like mist. A quantum fog permeating everything. There would be trillions upon trillions of them in every cubic centimetre, moving slowly, barely interacting with anything. Together, all these tiny, nearly massless particles could add up to the mass we're looking for. It's a strange idea, perhaps, but dark matter has always been strange. We're looking for something invisible, after all. Strange seems appropriate. Sterile neutrinos are yet another possible form of dark matter. Then there are sterile neutrinos, regular neutrinos we know about. They're produced in nuclear reactions, streaming out from the sun and from supernova. But sterile neutrinos, if they exist, would be even more elusive. They wouldn't interact through any of the known forces except gravity. Completely sterile, completely hidden. They'd be heavier than regular neutrinos, but still lighter than WIMPs, occupying a middle ground between hot and cold dark matter. Some theories predict they should exist. Some experiments have hinted at anomalies that could be explained by them. But like everything else with dark matter, certainty remains just out of reach. Each particle candidate explains some observations, but not all of them. Here's the challenge. Every candidate for dark matter can explain certain things. WIMPs work well with many observations. Axions solve some theoretical problems in particle physics. Sterile neutrinos fit certain anomalies, but none of them perfectly explains everything. There are always edges that don't quite line up, observations that require additional assumptions, details that remain unclear. It's possible that dark matter is made of just one type of particle. It's also possible that it's a mixture, several different kinds working together. The universe doesn't owe us simplicity. Sometimes the answer is messier than we'd like. Physicists build detectors deep underground to search for dark matter particles. To catch a ghost, you need a quiet place. That's why dark matter detectors sit deep underground, beneath mountains, in old mine shafts, surrounded by kilometres of rock. Not to hide them, but to shield them. Up on Earth's surface, cosmic rays constantly rain down, creating background noise that would overwhelm any signal. Particles from space crash into the atmosphere, producing showers of secondary particles that trigger detectors constantly. But deep underground, that noise fades. The rock filters it out. In the stillness of these subterranean laboratories, scientists wait, watching, hoping for a signal that isn't noise. Experiments like LUX, Xenon NT, and Panda X use tanks of ultra-pure liquid xenon. The detectors themselves are marvels of engineering, tanks filled with liquid xenon purified to extraordinary levels, chilled to frigid temperatures, wrapped in sensors that can detect the faintest flash of light. Xenon is used because it's dense and heavy. If a dark matter particle collides with a xenon nucleus, the nucleus recoils, producing a tiny spark of light and a pulse of electrical charge. The sensors catch this signal. At least that's the hope. The entire apparatus sits inside multiple layers of shielding, protected from every possible source of interference, waiting in the dark for something darker to announce itself. These detectors watch for tiny flashes of light that might occur when a dark matter particle collides with a xenon atom. The collision they're looking for would be incredibly rare. Dark matter particles supposedly pass through ordinary matter all the time without interacting. That's the whole problem. But occasionally, very occasionally, one might bump into a nucleus. Just one collision out of trillions of particles passing through. That collision would produce a flash of light lasting only nanoseconds, releasing just a few photons. It would be one of the smallest signals imaginable, and yet, with sensitive enough equipment, it might be detectable. It might be the first direct evidence of dark matter's particle nature. That's what these experiments are waiting for. A whisper in the silence. Despite decades of searching, no experiment has definitively detected a dark matter particle. The detectors run, the data accumulates, years pass, and so far nothing conclusive. There have been hints, anomalies, signals that look promising for a while before being explained away or failing to replicate, but no definitive detection. No moment where scientists could say, with confidence, we found it. This doesn't mean dark matter doesn't exist. The gravitational evidence remains overwhelming. It just means that whatever dark matter is, it's even more elusive than we hoped. More weakly interacting, more ghostly, harder to catch than our current technology allows. The search continues with ever more sensitive instruments, but the search doesn't stop. New detectors are being built, larger and more sensitive than before. Experiments run longer, gathering more data, reducing background noise to even lower levels. Scientists refine their techniques, test new materials, explore different energy ranges. The hunt for dark matter particles has become one of the great ongoing efforts of modern physics. It requires patience, persistence, and a willingness to spend years, maybe decades, looking for something that might only reveal itself in the faintest possible way. Somewhere in the dark, deep underground, beneath mountains and lakes and ancient rock, the detectors wait. They'll keep waiting. Because the alternative, giving up on understanding what makes up most of the universe, isn't really an option at all. But what if dark matter doesn't exist? What if instead of adding invisible substance to the universe, we've simply misunderstood how gravity works? Some physicists take this possibility seriously. They propose that at galactic scales, gravity might behave differently than Einstein predicted. Perhaps the universe doesn't need dark matter at all. Perhaps it needs different physics. This is science at its best, entertaining the possibility that our fundamental assumptions might be wrong, not dismissing evidence, but questioning whether we're interpreting it correctly. It's worth considering. After all, we've been wrong before about how the universe works. Some scientists propose modifying Einstein's gravity equations instead of adding dark matter. These theories go by names like MOND, which stands for Modified Newtonian Dynamics, or TVS, a relativistic version that tries to work with Einstein's framework. The basic idea is simple, or at least conceptually simple. Maybe gravity doesn't follow an inverse square law at very large distances. Maybe it weakens more slowly than we think, creating extra gravitational pull without requiring extra mass. If you adjust the equations just right, you can make galaxies rotate the way we observe them rotating, all without invoking invisible matter. It's elegant in a way, one change to the rules instead of adding a whole new type of substance. These theories are called MOND or TVS. MOND has been around since the 1980s. It works surprisingly well for individual galaxies. When you apply its modified gravity to spiral galaxies, their rotation curves come out right. No dark matter needed, The math just works. For a while this seemed promising, maybe even revolutionary. But science requires more than explaining one type of observation. It requires explaining everything, and that's where modified gravity starts to struggle. It does well with galaxies, less well with other phenomena. The universe, it turns out, is more complicated than any single modification can handle. Modified gravity works well for individual galaxies, but struggles to explain galaxy clusters and cosmic structure. When you look at galaxy clusters, those enormous collections of hundreds or thousands of galaxies, modified gravity doesn't quite work. The gravitational lensing is too strong. The way galaxies move within clusters requires more mass than modified gravity can provide. And when you look at the largest scales, at the cosmic web and the distribution of galaxies across billions of light years, MOND really struggles. The patterns we observe, the clustering and the voids, they match what we'd expect from cold dark matter. They don't match what modified gravity predicts. One theory might explain galaxies, but it takes dark matter to explain the whole universe. Some theories propose dark matter might be a field permeating space rather than particles. There are other alternatives too. Maybe dark matter isn't made of particles at all. Maybe it's a field, something like the Higgs field that gives particles their mass, but different. A field that fills space, invisible and intangible, but with gravitational effects. Fields can have strange properties. They can clump and flow in ways particles can't. They can interact with themselves, creating structures on their own. It's speculative, certainly, but the line between particle and field in quantum physics is blurrier than you might think. Sometimes they're almost the same thing, viewed from different angles. Others suggest hidden extra dimensions could be influencing gravity in ways we don't understand. And then there are ideas that really push the boundaries, hidden dimensions, for instance. String theory predicts that space might have more than the 3 dimensions we experience. Maybe gravity can leak into these extra dimensions in ways we haven't accounted for. Maybe what looks like dark matter is really just gravity behaving strangely because it's spreading into places we can't see. It's the kind of idea that sounds like science fiction. But at the frontiers of physics, the line between science and fiction gets surprisingly thin. We're dealing with aspects of reality so far from everyday experience that even the wildest ideas deserve consideration. A few models try to combine both dark matter and modified gravity. Some physicists don't want to choose. They propose hybrid models that include both modified gravity and some amount of dark matter, maybe less than the standard model requires, but still present. These models try to capture the successes of both approaches while avoiding their weaknesses. It's a reasonable strategy, perhaps. Nature doesn't have to be simple. It doesn't have to fit into clean categories. The universe could be running on rules that combine elements we haven't even imagined yet. The truth might be more complex than either pure dark matter or pure modified gravity. So far, none of these alternatives match observations as completely as particle dark matter does. Here's the thing, though. Despite all these alternatives, despite decades of effort to find a different explanation, the standard dark matter model still works best. It explains galaxy rotation. It explains cluster dynamics. It explains gravitational lensing. It explains the cosmic microwave background. It explains large-scale structure. It even predicted things we later observed. No alternative theory can match that track record. They each explain some things well, but they stumble elsewhere. Dark matter, mysterious as it is, remains the most successful explanation we have. That doesn't make it correct, necessarily, but it makes it compelling. The universe continues to present puzzles that challenge even our best theories, and yet puzzles remain. even within the dark matter framework, there are tensions, small-scale discrepancies, observations that don't quite fit the predictions. The centers of some galaxies look different than simulations suggest they should. Dwarf galaxies behave oddly. There are hints, whispers of incompleteness, even in our best models. This is normal in science. Theories are never perfect. They're approximations, descriptions that work until they don't. The fact that dark matter theory has rough edges doesn't invalidate it, but it does mean we're not done yet. We're still learning, still refining, still listening to what the universe is trying to tell us. Computer simulations' accuracy depends on assumptions about dark matter's true nature. When astronomers run simulations of galaxy formation, they have to make choices. How much dark matter is there? How does it interact with itself? How is it distributed in the early universe? These assumptions shape what the simulation produces. Different assumptions lead to different outcomes. Get the parameters right, and the simulation creates a universe that looks like ours. Get them wrong, and it doesn't. The simulations are powerful tools, but they're only as good as the physics we put into them. They test our theories, but they also depend on those theories being at least approximately correct. It's a kind of circular reasoning we can't entirely escape. Every new observation brings us closer to understanding, whether it confirms or contradicts expectations. But this is how progress happens, slowly, through accumulation. Each new telescope, each new detector, each careful measurement adds another piece to the puzzle. Sometimes the piece fits where we expected, sometimes it doesn't, and we have to rethink the picture. Either way, we learn. Whether dark matter is particles or fields or modified gravity or something stranger still, the path to finding out runs through observation, through patience, through the willingness to be wrong and try again. The universe doesn't give up its secrets easily, but it does give them up eventually to those who keep looking. Dark matter acts as the universe's gravitational skeleton. Think of dark matter as the framework beneath everything, the invisible structure that holds the universe in its current shape. Like a skeleton supporting a body, dark matter provides the architecture upon which everything else is built. Stars hang from it, galaxies spin within it, clusters gather along it. Without this hidden framework, nothing would be where it is. Nothing would hold together the way it does. The universe would collapse into formlessness or scatter into isolation. Dark matter is the scaffolding we can't see, but upon which all visible creation rests. Without it, galaxies would spin themselves apart, their stars flung into intergalactic space. Galaxies rotate fast. The stars at their edges move at hundreds of kilometers per second, sweeping through space in great circles. At those speeds, without enough gravity holding them in, they should fly away like sparks from a spinning wheel. The visible matter in a galaxy, all its stars and gas, isn't massive enough to keep them bound. They'd escape. The spiral would unravel. Stars would drift into the darkness between galaxies, alone and unanchored. But dark matter provides the gravity they need. It holds them in place, keeps them orbiting, maintains the structure. Without it, every galaxy we see would have torn itself apart billions of years ago. Dark matter's gravity has shaped cosmic architecture from the Big Bang until now. From the very beginning, dark matter was there. In the early universe, when everything was hot and dense and uniform, dark matter clumped first. It responded to gravity before ordinary matter could. It created the first seeds, the first concentrations of mass. Those seeds grew. Ordinary matter fell into them. Stars formed. Galaxies assembled. Clusters connected. Everything that followed, all the structure we see today, traces back to those early dark matter clumps. For over 13 billion years, dark matter has been shaping the cosmos, guiding where matter goes, determining what forms and what remains empty. Every star-filled sky we see exists only because of this invisible framework. Look up tonight. Every star you can see, every constellation, every distant galaxy visible through telescopes, they all exist in their current positions because dark matter arranged them there. The light reaching your eyes travelled through a universe structured by invisible mass. The patterns you see, the clustering of stars into galaxies, the grouping of galaxies into clusters, none of it would exist without dark matter. The night sky is a visible manifestation of an invisible architecture. What you see is only the decoration. The frame beneath is dark. Every atom in your body occupies its position in space because dark matter's gravity arranged it there. Here's an intimate fact. The calcium in your bones, the iron in your blood, the oxygen you're breathing right now, these atoms exist where they do because dark matter's gravity pulled them there. Billions of years ago, dark matter clumped first, creating gravitational wells. Hydrogen and helium fell into those wells. Stars formed and forged heavier elements. Those stars died and scattered their contents. Eventually, some of those atoms became you. You exist at this location in space and time because invisible matter arranged the universe this way. Your very existence is woven into dark matter's gravitational architecture. In the early universe, dark matter could clump together before ordinary matter cooled enough to do the same. In the beginning, ordinary matter was tied up in a hot, dense plasma. Photons and electrons bounced off each other constantly. Matter and radiation were coupled together, unable to separate, unable to settle into clumps. But dark matter doesn't interact with light or radiation. It was free to move, free to respond to gravity alone. So while ordinary matter remained hot and uniform, dark matter started gathering. It formed denser regions. It created the gravitational landscape. By the time ordinary matter cooled enough to fall freely, the wells were already dug. The foundation was already laid. Dark matter prepared the way. These early clumps became seeds where the first galaxies would eventually form. Those early concentrations of dark matter became nurseries. Hydrogen and helium gas drifted into them, drawn by gravity, accumulating over millions of years. The gas compressed, heated, and eventually ignited into the first stars. Those stars gathered into the first small, irregular galaxies. The galaxies merged and grew. Everything visible in the universe today can trace its lineage back to those early dark matter seeds. They were small at first, subtle over densities in an otherwise smooth cosmos. But they grew, they deepened, they became the birthplaces of light. Dark matter guided the formation of galaxy clusters and the filaments connecting them. As the universe expanded and evolved, structure grew on larger and larger scales. Dark matter clumped not just into galaxy-sized halos, but into enormous concentrations where hundreds or thousands of galaxies would gather. And between these clusters, dark matter stretched into filaments, threads of mass connecting one cluster to another. These filaments guided how matter flowed through the universe. They acted like highways, channels along which gas and galaxies moved. The cosmic web emerged, that beautiful, intricate network of structure, all shaped by dark matter's invisible hand. Galaxies formed at the densest intersections of the cosmic web, where dark matter was most concentrated. If you could see dark matter, the universe would look like a vast web of filaments, glowing threads crossing through space. Where those threads intersect, where multiple filaments meet, the density is highest, and that's where galaxies form. The brightest nodes in the cosmic web are the richest galaxy clusters, places where dark matter has concentrated into enormous masses. Galaxies don't appear randomly. They follow the web. They light up the intersections. They trace the invisible structure like light strung along a framework we cannot see. Without dark matter, the universe would be a nearly featureless expanse of diffuse gas. Imagine a universe without dark matter. After the Big Bang, matter spreads out uniformly. Gravity tries to pull it together, but there's not enough time, not enough concentration. The universe expands faster than structure can form. Hydrogen and helium drift through space, thinning out, never gathering into stars. No galaxies, no clusters, no cosmic web. Just a vast, dark, nearly empty expanse growing colder and more diffuse forever. It's a bleak picture, a sterile cosmos. Without dark matter's early clumping, without its gravitational pull holding things together, the universe would have no structure at all, no stars to forge heavy elements, no planets, no life. Just emptiness expanding into greater emptiness forever. Simulations like the Millennium simulation show dark matter's filaments forming the cosmic web over billions of years. Astronomers have built computer simulations that model the entire universe. The Millennium simulation is one of the most ambitious, tracking billions of particles through cosmic time, watching how structure emerges from the smooth early universe. When you run these simulations forward, letting dark matter respond to gravity over billions of years, something remarkable appears. Filaments, threads of dark matter stretching across space, connecting denser nodes, creating a vast network. The simulation doesn't impose this structure. It emerges naturally from the physics. Dark matter wants to form webs. It's written into the mathematics of gravity and expansion. The structure resembles a neural network, threads connecting nodes in a pattern that looks almost alive. When you look at maps of the cosmic web, it's startling how organic it appears. Filaments branching and connecting like neurons, dense nodes where filaments intersect like synapses, galaxy clusters forming where these nodes concentrate. The universe's large-scale structure looks like a brain thinking cosmic thoughts. Of course, it's not conscious, but the resemblance reminds us that nature creates similar patterns at vastly different scales, from neural networks in your brain to dark matter networks spanning billions of light years. Structure emerges wherever there's matter and gravity and time. The same rules apply, whether you're building a thought or building a cosmos. Dark matter's gravity slowed the universe's expansion slightly in its early history. In the beginning, the universe expanded rapidly, everything flying apart from everything else. But gravity works against expansion. It pulls matter together, trying to slow the separation. In the early universe, when matter was denser, this pull was stronger. Dark matter contributed to that pull. Its gravity tugged on everything around it, acting as a brake on expansion. Not enough to stop it, but enough to slow it down, to give structure time to form. Without this gravitational drag, the universe might have expanded too quickly for galaxies to assemble. Dark matter didn't just shape where things went, it shaped when they could form at all. Later, dark energy began dominating, accelerating the expansion instead. For billions of years, dark matter's gravity was winning the tug-of-war. Expansion slowed, structure formed, galaxies gathered into clusters. But around 5 or 6 billion years ago, something shifted. The universe had expanded enough that matter became more diffuse. Gravity's pull weakened, and something else took over. Dark energy, a mysterious force that pushes space itself apart, making the universe's expansion accelerate rather than slow. Now we live in an era dominated by dark energy. The expansion is speeding up. Galaxies are moving away from each other faster and faster. Dark matter still holds local structures together, but on the largest scales, dark energy is winning. Dark matter pulling together and dark energy pushing apart now shape the universe's evolution together. It's a cosmic tension. Dark matter trying to gather things into structure. Dark energy trying to spread everything apart. They're both invisible, both mysterious, both shaping the universe's fate in opposite ways. On small scales, inside galaxy clusters, dark matter wins. Gravity holds things together, but on large scales, between galaxy clusters, dark energy dominates. The space between structures grows. The cosmic web stretches. These two dark forces working against each other determine what the universe will become, whether it will keep expanding forever, growing colder and more isolated, or whether something else awaits. In the first moments after the Big Bang, the universe was unimaginably hot and dense. There were no stars, no atoms even, just energy and particles in a state so extreme we can barely model it. Then it expanded, cooled. After about 380,000 years, it cooled enough for electrons to bind to nuclei, forming the first neutral atoms. Light could finally travel freely, but for a long time after that, nothing glowed. The universe entered what astronomers call the cosmic dark ages. No stars yet, just neutral hydrogen gas drifting through space, filling the darkness. Dark matter was there too, already clumping, already preparing the stage for what would come next. Dark matter's role at each cosmic epoch was essential, even when invisible. During those dark ages, dark matter was working. Its gravity pulled gas into denser and denser concentrations. Slowly, over millions of years, the first stars began to form inside the deepest dark matter wells. These were massive stars, brilliant and short-lived, burning hot and fast. When they exploded, they began enriching the universe with heavier elements. More stars formed, small galaxies assembled, irregular and chaotic at first. Dark matter guided all of it. Every star that ignited did so inside a dark matter halo. Every galaxy that formed was cradled by invisible mass. The visible universe owes its existence to the invisible scaffolding beneath. The first stars formed in dark matter halos, the deepest gravitational wells in the early cosmos. Those first stars were unlike anything we see today, enormous, hundreds of times more massive than the Sun. They burned with incredible intensity, flooding space with ultraviolet light. They lived only a few million years before exploding as supernovae. But in that brief time, they changed everything. Their light began breaking apart neutral hydrogen atoms, ionizing the gas around them. This process, called ionization, gradually made the universe transparent again, and all of it happened inside dark matter halos. Without those gravitational wells, the gas wouldn't have compressed, the stars wouldn't have formed, the dark ages might have lasted forever. Reionization was driven by stars forming in dark matter concentrations. As more stars formed, as galaxies grew and merged, reionization spread. Bubble by bubble, region by region, the universe lit up. Neutral hydrogen became ionized. The fog cleared. Light could travel farther. This epoch, spanning hundreds of millions of years, transformed the cosmos from dark and opaque to bright and transparent. And it all followed dark matter's distribution. Where dark matter concentrated, stars formed first. Where it remained sparse, the darkness lingered longer. The universe didn't light up uniformly. It lit up along dark matter's invisible map, tracing the threads and nodes of the forming cosmic web. ongoing structure formation continues today, still guided by dark matter's gravitational pull. The universe hasn't stopped evolving. Galaxies still merge, clusters still grow. Gas still falls into dark matter halos, forming new stars in some regions. The cosmic web continues to sharpen, its filaments becoming more defined. Dark matter is still at work, still pulling, still shaping. The process is slower now than it was in the early universe. The expansion driven by dark energy makes it harder for structures to grow on the larger scales. But locally, within galaxy groups and clusters, dark matter still dominates, still builds, still writes the architecture of where matter goes and what it becomes. The early universe was dark matter dominated. Gravity ruled, structure formed. But the late universe is dark energy dominated, and that changes everything. In the early universe, when everything was closer together, dark matter's gravity was the dominant force. It shaped how the universe evolved, how structure formed, how galaxies assembled. But as the universe expanded, as space grew and matter thinned out, gravity's influence weakened. Dark energy, which stays constant even as space expands, gradually became more important. Now we live in a transitional era. Dark matter still matters locally, but cosmically, dark energy is taking over. The future belongs to expansion, to isolation, to structures drifting apart. The age of gathering is ending. The age of separation has begun. And we're here, floating in the middle of that transition, witnesses to a universe in the process of changing its fundamental character. Dark matter determines how fast galaxies rotate and how stable they remain. Inside every spiral galaxy, stars orbit the center at speeds that depend on how much mass is pulling on them. The more mass, the faster they move. But the visible stars and gas aren't enough to explain the rotation speeds we observe. Something invisible is adding mass, creating extra gravity, keeping those outer stars moving faster than they should. That something is dark matter. It determines the rotation curve. It sets the speed limit. And by keeping everything moving fast enough, it maintains the galaxy's stability. Without it, the spiral structure would slowly unwind, stars drifting away over billions of years. Dark matter is the hidden anchor. It anchors spiral arms and prevents stars from flying away. Spiral arms are beautiful, sweeping patterns of light and gas that curve through a galaxy. But they're not permanent structures. They're density waves. Patterns moving through the disk at a different speed than the stars themselves. Stars drift into the arms, brighten as gas compresses and forms new stars, then drift out again. But for this pattern to persist, for the galaxy to maintain its shape, there needs to be enough mass to keep everything gravitationally bound. Dark matter provides that mass. It creates the underlying potential that keeps stars orbiting predictably, that prevents them from gaining enough speed to escape entirely. The arms remain because the invisible framework holds. When galaxy clusters collide, their dark matter halos pass through each other almost unaffected. Galaxy clusters are the largest gravitationally bound structures in the universe. Thousands of galaxies held together by gravity, along with vast amounts of hot gas and enormous dark matter halos. When two clusters collide, it's one of the most energetic events in the cosmos. But collisions at this scale are strange. The galaxies themselves rarely hit each other directly. Space is too vast. They pass through like ghosts. The dark matter halos also pass through each other, barely interacting. Dark matter doesn't collide with itself in any significant way. It just keeps moving, sliding through the collision like it wasn't even there. The bullet cluster shows two galaxy clusters that collided 150 million years ago. There's a particular collision that astronomers love to talk about. It's called the bullet cluster, and it's one of the best pieces of evidence we have for dark matter's existence. About 150 million years ago, two galaxy clusters smashed into each other at tremendous speeds. From our perspective, we're seeing the aftermath, the wreckage of that collision frozen in time by the vast distances involved. The light we see left that cluster long ago, carrying with it a record of what happened when two of the universe's largest structures met. Visible gas slowed down during collision due to friction, but the dark matter didn't. Here's what makes the bullet cluster so interesting. When the clusters collided, the hot gas that fills the space between galaxies in each cluster slammed together. Gas can collide. It creates friction, heat, shock waves. The gas clouds from each cluster slowed down dramatically, heating up and glowing in X-rays as they interacted. You can see this in observations. There's a bright region of X-ray emission where the gas piled up and stopped. But something else didn't stop. Something passed right through the collision zone without slowing down at all. That something was dark matter. Gravitational lensing maps show where the mass actually is, and it's where the dark matter went, not where the gas stopped. Astronomers can map where the mass is in the bullet cluster by looking at gravitational lensing. Light from distant galaxies behind the cluster gets bent as it passes through, distorted by gravity. By measuring how much the light bends, they can figure out where the mass is located. And here's the remarkable thing. The mass isn't where the gas is. The gravitational lensing shows most of the mass has separated from the visible matter. It's ahead of the gas, on the far side of the collision, exactly where you'd expect it to be if dark matter passed through without interacting. The mass went one way, the gas went another. You can see the separation clearly. This is some of the most direct evidence that dark matter behaves like ghostly particles passing through ordinary matter. It's hard to overstate how important this observation is. The bullet cluster shows, visually and measurably, that most of the mass in galaxy clusters is not where most of the visible matter is. Something invisible separated from the gas during the collision. Something that only interacts through gravity, not through friction or electromagnetism or any other force. This is exactly what particle dark matter should do. It should pass through collisions unaffected, leaving the ordinary matter behind. And that's precisely what we see. It's about as close to catching dark matter in the act as we've gotten. The bullet cluster image convinced many remaining skeptics that dark matter is real. Before the bullet cluster, some astronomers still wondered if modified gravity could explain everything. Maybe we didn't need dark matter at all. Maybe we just needed different equations. But the bullet cluster made that position much harder to hold. How do you modify gravity to make mass appear in one place, while matter sits in another? How do you explain a gravitational field that's separated from the stuff creating it? Modified gravity theories struggle to account for what the bullet cluster clearly showed. Dark matter, on the other hand, explained it perfectly. After the bullet cluster observations were published, the scientific consensus around dark matter grew even stronger. It became harder to argue against something you could almost see in the separation of mass and light. There are other colliding clusters too, each one adding to the evidence. The bullet cluster isn't unique. Astronomers have found other examples of colliding galaxy clusters that show the same effect. The mass and the gas separated during collision. Every time the pattern is consistent with dark matter passing through, while ordinary matter gets left behind. Each new observation strengthens the case. Each new collision provides another test of the theory. and each time dark matter passes the test. The universe keeps showing us the same thing in different places, with different clusters, at different distances. The message is clear. Something invisible and massive is out there, moving through space, interacting only through gravity. We've seen its fingerprints in collision after collision, written in the bending of light and the separation of mass from matter. Dark matter might weakly interact with itself, potentially changing halo shapes over cosmic time. Most models assume dark matter particles pass through each other without interacting at all, completely collisionless. But some physicists wonder if dark matter might interact with itself just a little. Not with ordinary matter, but with other dark matter particles. If these self-interactions exist, even weakly, they could affect how dark matter halos form and evolve. The centers of halos might be less dense. The shapes might be rounder. Over billions of years, these subtle interactions could leave traces in the distribution we observe. It's another variable to consider, another possibility that could refine our understanding. The search for dark matter includes searching for how it behaves with itself. Each new observation refines our understanding of what dark matter does. Even though we don't know what dark matter is, we're learning more about what it does, how it clumps, how it surrounds galaxies, how it responds to collisions, how it shapes structure on different scales. Every telescope, every survey, every measurement adds detail to the picture. We're mapping dark matter's behavior, even without seeing the substance itself. It's like studying wind by watching leaves move. You can learn about patterns, about flow, about strength and direction, all without ever seeing the wind directly. Dark matter reveals itself through its effects, and those effects are becoming clearer with time. We've mapped dark matter's distribution across the universe without knowing what it is. This is one of the stranger achievements of modern astronomy. We've created maps of something we cannot see, cannot touch, cannot detect directly. Maps showing where dark matter concentrates, where it forms filaments, where it creates the cosmic web's nodes and threads. These maps come from gravitational lensing surveys, from galaxy motion studies, from the cosmic microwave background. They're assembled from indirect measurements, from watching how dark matter's gravity affects light and matter, and yet they're remarkably detailed. We know where dark matter is, even if we don't know what it is. It's a peculiar kind of knowledge, but knowledge nonetheless. Its presence whispers through gravity alone, bending light, holding galaxies, shaping structure. Dark matter speaks only one language: gravity. It doesn't emit signals we can decode. It doesn't leave trails we can follow. It doesn't interact with instruments we've built. But it pulls, it bends space, it curves the paths of light and matter passing through its presence. That gravitational whisper is how we know it's there. Subtle, persistent, undeniable. Every galaxy that spins too fast is whispering about dark matter. Every cluster that bends light too strongly. Every filament in the cosmic web. The universe is full of these whispers if you know how to listen. The James Webb Space Telescope may reveal new clues about dark matter's role in early galaxy formation. JWST is now peering at the universe's earliest galaxies, some forming just a few 100 million years after the Big Bang. These ancient galaxies exist because dark matter formed halos first, creating gravitational wells where gas could collect and stars could ignite. By studying how these first galaxies formed, grew, and evolved, we're really studying dark matter's role as cosmic architect. Every early galaxy JWST discovers tells us something about the invisible scaffolding that made its formation possible. The telescope can't see dark matter directly, but it sees dark matter's consequences written in the structure of ancient light. The Euclid Space Telescope will map dark matter's distribution across billions of light years. Euclid launched with a specific mission: to map the geometry and structure of the universe across vast cosmic distances. It will survey billions of galaxies, measuring their shapes, their positions, how their light gets distorted by intervening mass. From these measurements, astronomers will reconstruct the distribution of dark matter across enormous volumes of space. It's a census of the invisible, mapping where dark matter concentrates and where it remains sparse. These maps will help test theories about dark matter's nature, about how structure forms, about how the universe evolved. Euclid is building a three-dimensional portrait of darkness itself. Next-generation underground detectors are becoming sensitive enough to detect even rarer particle interactions. The hunt continues in those deep underground laboratories. New detectors are being built, larger and more sensitive than before. Some use even more xenon. Others try different materials, different approaches. The sensitivity improves with each generation. They're reaching thresholds where, if dark matter particles interact even extraordinarily rarely with ordinary matter, they might finally see something. A single collision, a flash of light, a recoil. It would need to happen just once in a tank of liquid watched for months or years. Just once, clearly enough to distinguish from background noise. That's what they're waiting for. That's what decades of work have been building toward. Perhaps we'll finally detect dark matter's particle nature in the coming decades. There's cautious optimism in the physics community. The detectors keep improving. The sensitivity keeps increasing. The noise keeps decreasing. Maybe, in the next 10 or 20 years, one of these experiments will catch something real. Maybe we'll finally know what dark matter is made of, not just what it does. It would be one of the great discoveries of the century, confirming decades of theory, identifying a substance that makes up most of the universe's mass. It would open new fields of physics, answer old questions, and probably raise entirely new ones. But that moment hasn't arrived yet. For now, the search continues, patient and methodical, waiting for the universe to give up one of its deepest secrets. Or perhaps we'll discover it's something stranger than particles, a field, a modification of space-time, or something we haven't imagined yet. But there's also the possibility that we're wrong about what we're looking for. Maybe dark matter isn't particles. Maybe it's a field permeating space, something more diffuse and distributed. Maybe it's a property of space-time itself, gravity behaving strangely in ways we haven't understood. Maybe it's something we haven't even conceived of yet, something that requires new physics, new mathematics, new ways of thinking about reality. Science has surprised us before. Quantum mechanics seemed impossible until it wasn't. Relativity seemed absurd until it was proven. Dark matter could be another revolution waiting to overturn our assumptions. The search itself has value regardless of what we find. Even if we never detect dark matter particles directly, the search teaches us things. It pushes technology forward. It forces us to think carefully about what we know and what we assume. It reminds us that the universe is under no obligation to reveal itself easily. The decades spent building detectors, analyzing data, and refining theories aren't wasted, even if they don't produce the discovery we hoped for. They're part of the process, part of how science works. We ask questions, we build tools, we look carefully. Sometimes the answer comes quickly. Sometimes it takes generations. But the looking itself, the careful patient searching, that's what moves us forward into deeper understanding, one measurement at a time. The visible universe rides upon dark matter like foam on an ocean. Everything you can see, every star and galaxy, every nebula glowing in photographs, every wisp of gas lit by radiation, all of it floats on something deeper. Dark matter is the ocean beneath, vast, dark, mostly still. The visible universe is just the surface layer, the bright foam catching light, dancing with motion and colour. But beneath it lies the true substance, the foundation that holds everything up. We live on the surface of this ocean, seeing only the spray and shimmer, while most of the depth remains hidden below. Every galaxy, every star, every breath of light depends on it. Nothing luminous exists independent of dark matter. Every galaxy spins within a dark matter halo. Every star formed in a gravitational well that dark matter created. Every photon of light traveling through space moves through a universe shaped by invisible mass. Light itself, the thing we use to see and understand the cosmos, owes its existence to dark matter's gravitational architecture. Without dark matter, there would be no stars to emit light, no galaxies to contain them, no structure at all, just darkness and diffuse gas spreading through an empty, expanding void. Light depends on darkness. Visibility depends on the invisible. It's a strange relationship. And yet dark matter remains fundamentally invisible to us. We've never seen it, not directly, not with any instrument we've built or any wavelength we've examined. It doesn't glow, it doesn't cast shadows, it doesn't block light or bend it through interaction, only through gravity. We infer its presence from what it does, from how it moves other things, from the patterns it creates in structure and motion. But the substance itself remains hidden. After decades of searching, after countless observations and measurements and theoretical refinements, dark matter remains as invisible as it was when Zwicky first proposed it. We know more about what it does, but we still don't know what it is. It is the silent foundation beneath all of creation. If you could strip away everything visible from the universe, remove all the light and matter we can detect, what would remain? The skeleton, the structure, the gravitational framework upon which everything else was built. Dark matter would still be there, holding its shape, maintaining its web of filaments and nodes. The cosmic architecture would persist even without anything to illuminate it. Dark matter is the stage. Ordinary matter is the performance. We focus on the performance because it's what we can see, what we can measure directly. But the stage came first. The stage makes the performance possible. The foundation is always there, silent and invisible beneath everything that shines. We are the bright dust of a hidden world. Think about what you are. Atoms forged in stars arranged into conscious patterns, capable of contemplating your own existence. You are made of ordinary matter, the substance that emits light, that interacts, that can be seen and touched. You are bright matter in a dark universe. Everywhere around you, invisible substance holds everything together. You are a luminous exception in a cosmos dominated by darkness. And somehow, through science and patient observation, you, bright dust that you are, have discovered the hidden world you're part of. We are the universe's rare gift to itself, matter that shines both literally and metaphorically, capable of perceiving the imperceptible, bound together by what we cannot see. Everything in your life, every person you know, every place you've been, exists where it does because dark matter's gravity arranged it that way. The planet beneath your feet orbits a star that formed in a dark matter halo. That star moves through a galaxy, held together by invisible mass. The galaxy drifts through a universe structured by dark matter from its beginning. You are bound to your place in space and time by forces you cannot see, held in position by gravity emanating from substance you cannot detect. It's humbling, perhaps, or maybe comforting. Either way, it's true. The invisible binds all visible things together, floating on an invisible web that holds the cosmos together. The cosmic web stretches across billions of light years, filaments of dark matter connecting clusters, threading through voids, creating the largest structure in existence. And somewhere on one of those filaments, in a relatively quiet region, in a fairly ordinary galaxy, on a small rocky planet orbiting an unremarkable star, you exist. You're floating on that web too, part of its structure, connected through gravity to everything else, however distantly. The web is invisible, but it's there. It's always been there. It was there before you were born and will remain long after you're gone. You are a temporary brightness, a brief moment of consciousness, floating on an eternal, invisible structure. The mystery continues, vast, quiet, and perhaps eternal. We've come far in understanding dark matter. We know it exists. We know roughly how much there is. We know how it clumps and where it concentrates. We know its role in forming galaxies and shaping the cosmos, but we don't know what it is. That central question remains unanswered. Maybe we'll solve it in the coming years. Maybe it will take generations. Maybe, and this is worth considering, maybe we'll never fully understand. Some mysteries resist solution. Some questions remain open no matter how carefully we look. Dark matter could be one of those, not because we're not trying hard enough, but because the universe doesn't owe us complete knowledge. Mystery is part of existence. Perhaps it always will be. What does it mean to live in a mostly invisible universe? It means the world is stranger than it appears. It means most of what exists is hidden from direct perception. It means we're surrounded by things we can only understand indirectly, through their effects, through careful reasoning and measurement. It means the universe is teaching us humility. We are not the main component of reality. Ordinary matter, the stuff we're made of, is a minority, a small exception. The universe is mostly dark, mostly invisible, mostly made of something we cannot directly observe. And yet, here we are, part of that universe, trying to understand it, succeeding more than we might expect, given how much is hidden from us. We are made of the cosmos's minority substance. Only 5% of the universe is ordinary matter. Everything else is dark matter and dark energy, which means you, made entirely of ordinary matter, are incredibly rare. You're built from the unusual stuff, the bright matter, the interactive matter, the matter that can form complex structures like brains and bodies and consciousness. Dark matter can't do that. It can only pull gravitationally. It can't bond into atoms, can't form molecules, can't create chemistry or biology or thought. In a universe dominated by darkness, you are a remarkable exception, a concentration of the rare substance that can not only exist, but know that it exists. Ordinary matter is extraordinary in its rarity. We call it ordinary because it's what we're familiar with, but familiarity doesn't mean common. Ordinary matter is actually the strange one in this universe, the oddity, the exception. Most of the cosmos is dark matter, silent and simple, interacting only through gravity. But ordinary matter does more. It creates light, it forms stars, it makes planets, it produces life and consciousness and everything we call civilization. It's extraordinary, not despite being ordinary, but because being ordinary in this universe means being capable of complexity that dark matter can never achieve. We are ordinary in the most extraordinary way possible. The beauty of mystery in an age demanding answers. We live in a time that values certainty. We want answers. We want to know. And science provides many answers, solves many mysteries, explains much of what once seemed inexplicable. But some mysteries remain. Dark matter is one of them. And maybe that's not a failure. Maybe mystery has its own value. It reminds us how much we don't know. It keeps us curious. It gives us something to reach toward. A universe fully explained might be a universe less interesting to inhabit. The mystery of dark matter is frustrating for physicists who want to solve it, certainly. But for the rest of us, for anyone who looks up at night and wonders, maybe the mystery is part of the beauty. Maybe not knowing is what makes the search meaningful. How dark matter changes our perspective on existence. Before we knew about dark matter, we thought the universe was mostly what we could see. Stars and galaxies and empty space between them. But now we know better. Now we know that most of the universe is invisible, that most of what exists refuses to interact with light. This changes how we understand reality. It suggests that what we perceive directly is just a small fraction of what's real. It implies that the universe is far stranger than our senses suggest. It teaches us that understanding requires more than looking. It requires thinking, measuring, inferring. Dark matter has expanded our cosmology, deepened our sense of how reality works, and humbled us in ways we needed. The mystery continues, vast, quiet, and perhaps eternal. 100 facts about dark matter, 100 pieces of a puzzle that's still incomplete. We know so much now compared to when Zwicky first proposed his dark matter. We've measured it, mapped it, watched it shape galaxies and bend light. We've built our cosmology around it. And yet the central question remains, what is it? That question sits at the heart of modern physics, unanswered, waiting. Maybe one day we'll know. Maybe a detector will flash. Maybe a theory will crystallize. Or maybe the mystery will persist, outliving us all, a quiet reminder that the universe contains depths we cannot fully fathom. Either way, the search continues, the wonder remains, and somewhere out there, in the space between stars, dark matter drifts on, invisible and patient, holding everything together. And now the stars begin to dim behind your thoughts. We've drifted through 100 quiet truths about the invisible universe, from Fritz Zwicky's dismissed calculations to Vera Rubin's patient measurements, from computer simulations revealing cosmic webs to underground detectors waiting in the dark, from the bullet cluster's separated mass to the philosophical questions about what it means to live in a mostly hidden cosmos. 100 facts, each one a window into something we cannot see but know is there. When you look up at the darkness tonight, understand it differently now. The space between stars is not empty. It's full of dark matter, threading through everything, holding galaxies together, maintaining the structure that makes starlight possible. The darkness is not absence, it's presence. Most of the universe exists in that darkness, invisible but essential, silent but active. The space you thought was void is actually the foundation. What seemed like nothing is actually everything. We've travelled together through the whole story. The early mystery and rejection, the mounting evidence that couldn't be ignored, the realization that galaxies need invisible mass to hold together, the mapping of dark matter halos surrounding every galaxy, including our own, the cosmic web stretching across billions of light years, the first stars forming in dark matter's gravitational wells, the bullet cluster showing mass and matter separated, the ongoing search in laboratories buried deep underground, and finally, the philosophical weight of knowing we're made of the universe's minority substance, floating on an invisible foundation we may never fully understand. Dark matter is the foundation of everything we love, every star you've ever wished upon, every planet that might harbour life, every galaxy photographed by telescopes, every atom in your body. All of it rests on dark matter's invisible structure. The people you care about exist because dark matter created the conditions for stars to form and planets to assemble. The beauty you see in the night sky exists because dark matter holds it in place. Everything you value, everything that brings you wonder or comfort or joy, floats on a sea of invisible mass that was there before stars existed and will remain long after they're gone. The search continues, patient and determined. Right now, deep beneath mountains, detectors wait in the dark. Tanks of liquid xenon surrounded by sensors, watching for the faintest flash that might mean a dark matter particle just collided with an atom. In space, telescopes like James Webb and Euclid map the early universe and measure the cosmic web, tracing dark matter's influence across billions of years. Scientists refine theories, build new instruments, and pursue the mystery with quiet persistence. The answer might come tomorrow or in 50 years. But the search itself is beautiful. Humanity reaching toward understanding, even when understanding seems impossibly distant. Tonight, when you look up at the stars, you'll know something most people who've ever lived didn't know. You'll know that most of what holds the universe together is invisible, that the stars shine because of something we cannot see, that you're floating inside a dark matter halo right now, surrounded by substance that passes through you without touching, holding your galaxy together with gravity alone. The universe is stranger and more wonderful than our ancestors imagined, more mysterious than it appears, more full of invisible architecture than visible light. Science hasn't diminished the mystery, it's deepened it. We know so much more than we did a century ago. We've measured dark matter's effects, mapped its distribution, watched it shape galaxies and bend light. And yet the central question remains, what is it? That unanswered question makes the universe more mysterious now than when we thought we understood it. Science reveals beauty through mystery. It shows us how much we don't know while teaching us how to look more carefully. Perhaps not knowing is the most beautiful fact of all. Perhaps the search is more important than the answer. Perhaps wonder is what we're really after. You are bright matter in a dark universe, rare and luminous, capable of thought and curiosity and love, made of atoms forged in stars, arranged in patterns complex enough to contemplate the invisible cosmos. You're part of something vast and mostly hidden. And somehow, despite being made of the minority substance, despite living on a small planet in a quiet corner of an ordinary galaxy, you've discovered the universe's invisible skeleton. That's remarkable, that's beautiful, that's worth carrying with you as you drift towards sleep. This is the sleepy astronomer, wishing you sweet dreams under invisible stars. Rest well knowing that dark matter holds everything together, including you. The universe is stranger than you imagined, more wonderful than it appears, and more mysterious than it will probably ever reveal. And that's exactly as it should be. Good night.